So, good morning, ladies and gentlemen. So we come to the third part of my short series of lectures about particle therapy using proton and ion beams. Today, I skip to the topic daily operations and future concepts. So a story from what is going on today, what is the next future, and maybe what will come in 20 years. Just a short outline of the talk of today. I will start with some slides about the daily operations, experience from the first 5 years at HIT during the operation and the commissioning and operation of the machine. As I noticed, we have already treated now 1,000 patients. This was a number in July this year. But we are also thinking on future enhancements for synchrotron-driven particle therapy facilities. One can save a lot of time in the synchrotron cycles, and I will show some examples where we are working on and others. And this is magnetic field control and feedback, dynamic spill shaping, multi-energy operation within one cycle. These are the topics. And the last part of my talk of today will be an outlook to new accelerator concepts, which are discussed in the moment: FFAGs, laser plasma accelerators, dielectric wall accelerators, and I will have a short section to superconducting gantries also. Okay, at HIT, everything starts with the commissioning by GSI. We started in 2006. At that time, I was still at GSI, with the commissioning of the ion sources in the LINAC. And then there was a break at the beginning of 2007. Meanwhile, in 2005, a company was founded as a daughter of the university hospital company, and well, there were only a few people at the beginning, and then we have to step over to make the operation by this small company. So GSI did the commissioning, it helped a little bit, and then there was a handover of the first part, and a year later, when we had the beam first in the synchrotron and then at the first treatment place in March 2007, then also a year later, the handover took part for the synchrotron and high energy beam transfer lines. Well, we got a key for the LINAC and a certificate for the rest. And well, what to do then? So in 2007 and 2008, these were my first years at HIT. The main task was to set up the accelerator team. So as you see, there was a small core team hired in 2004-05, but then we have to build up the team. And it may be unusual, but the case is that we had only a third of the people which worked at HIT later on came from accelerator and institutes in before. The rest comes from industry. So we had to do an intense training of this team. This was done by GSI people. We involved also the companies which installed their systems in our house. We made in-house training within the HIT team itself, and so on and so on. This was a very intense phase to do that. And then we formed the internal organization of HIT, and I can show you what is the team of today. So, okay, I'm the head. Then we have 3 expert teams that we formed, and all these 3 teams also form a team which is on duty if we need one of them. So we put together all the. Let's come from the right side. So we had one team which is clearly responsible for the control system, for all the interlocks, for the radiation protection system, personal safety systems. So they fit together, 2 physicists and 3 technicians. The second team is everything around the RF, power supplies, cavities, and the linked infrastructure. These are 2 engineers and 3 technicians. And then there is all the rest together in one team, which is a little bit larger than 6 people, 1 physicist, 3 engineers, and 2 technicians. They care about the ion sources, beam diagnostics, vacuum magnets, and also the gantry. In total, we are now 20 employees, and 1/3 are physicists, 1/3 are technicians, a little bit less engineers in this, but it's always a third, more or less. And 3 physicists are not involved in any of these groups. They have special tasks. As an example, it's radiation safety, where you have to keep one man away from all the other 2 teams. Well, and we added now 2 students, which help our operation team in the weekends and nights. Okay, so we come back. The next, what we have to do is, when I came to HIT, there was only a shift operation which takes place in 2 shifts, early and late shift on 5 days. So we have to come over to a regular shift operation with 24 hours, 7 days a week. And well, this came up when the team becomes larger and larger. And then we took over more and more commissioning steps. And then the commissioning also of the therapy control system started. And in that time, the HIT operating crew did all the operation of the accelerator. Okay, but also troubleshooting had to be done in these first 2 years. It's clear if you install a lot of things, not everything is working well. So you can see a destroyed magnet connection box here, which burned. But such a magnet box is a nice thing because you have water and current in, so when the hose is burned, the water comes out and they are self-distinguishing. So you see the water comes out, so we have to repair such troubleshooting things also, and we got this within 2 days, so there was no big break in the commissioning. Well, then let's go to 2009. Having the goal to irradiate the first patient at the end of this year, we had to establish a routine operation of the accelerator. Especially the consolidation of the control system took the most time in this year. You can see my colleagues here in the control room, and we have to debug a lot of things. But okay, at the end it went stable. The achieved availability that we had at the end of the year, it was 98% in average. And we have had until today no longer breaks than 3 hours at daytime. At daytime is necessary because there is a patient treatment. We had longer stops in the night, but this does not affect the patient treatment. So we want to keep this because this is the limit to disturb not too much the patient treatment. Okay, we also introduced the daily accelerator quality assurance. So this is a slide, a screenshot of this procedure which we do every day. We may do intensity checks versus the energy, versus the intensity steps, if they are within the limits. The most used intensity steps are more here in this region, so everything is okay. It still stays within the limit. We do the same for position and profiles at the treatment places. This takes roughly half an hour to 40 minutes any morning. We'll come to that later. And what we get out after some months of operation, we found that retuning of the LINAC, the synchrotron, and the high energy beam transfer line must be done only every 3 to 4 months. only the intensity from the ion sources that had to be readjusted, sometimes daily, sometimes weekly. So it depends. After maintenance days, you have to readjust the intensity, let's say, in the first 3-4 days after the maintenance daily, and then the intervals get bigger and bigger. Okay, and this is a team which was there on the 15th November 2009 when we started treatment in one horizontal room. It was on a Sunday. The first patient, 2 patients were treated at that day, and you can see the pro team which was there on that day. And well, okay. Yeah, so let's come to the next 2 years, 2010 and 2011. They were dedicated to the gantry project within HIT as a third treatment place. There were some commissioning steps done already in 2008 by GSI, but they had to be stopped because we had some really severe problems with the drag chain. So we have to bring about 1 megawatt for the maximum energy of power to the magnets on the gantry. So you can imagine there is a big drag chain with a lot of power cables, and we suffered a lot from friction problems and damaging of cables. And it took us nearly 2 years to bring that out time by time. This was in parallel to other activities, bringing into operations the second horizontal treatment room and so on. So unfortunately, it took a little bit of tough time, but nevertheless, the overall HIT schedule does not suffer from that. Okay. The beam optical commissioning says that you need 37,000 settings per ion in the control system for the gantry, but fortunately you need only 1 to 2% of interpolation points that you have to tune in more semi-automatically, and the rest is then done by an optical code and interpolation. But nevertheless, we found out that we had a lot of problems because the parameters which we found to be fulfilled are a lot. So the optics is totally different in the horizontal place because we have the last 90-degree bending magnet. We found out that the vacuum chamber was a limit for the beam, and in the first calculations, the strong edge focusing of this magnet was, I would say, misunderstood. So we found that we could not irradiate 20 by 20 centimeters, but 18 by 18 now. Okay. So this is achieved now. The possible treatment field is now 180 by 180. What we do now is to look on the long-term stability, and for the proton beam, I can say it's pretty good. Carbon beam is under monitoring more now. And what you can see here, it was done by one of the Siemens guys who commissioned the irradiation technique. He put a photo of the gantry and then made a sketch of it. And with a pencil beam on the gantry, he painted this in a film. And you can see that you can really make it with very small doses in a very limited area. Okay, so yeah, this is the internal joke. 2012, year of the gantry. The patient treatment should start now mid-end of October. But in parallel, we did another thing this year. So this comes from our experience in the last years, especially in summer 2011. When we have a longer shutdown, it was a shutdown of 2 weeks plus the restart of the machine and the quality assurance of the medical physicists. What you can see is in the middle, on average, we had in before 35 patients per day treatments in 2 rooms at that time. then you have to ramp out because you have to phase out the patients and you lose a lot of treatment capability at that time by ramping down and also by ramping up the patients before and after the maintenance. And well, this is our boss came to us and asked, is it possible to do it in another way? And well, what we do now is we shorten the shutdowns to 4 days. Effectively for the maintenance it's 2.5 days. The rest is then for restarting the machine, doing the quality assurance, and so on and so on. And well, but we enlarged a little bit the number of these shutdowns, so we do it now every 2 months. And well, this is a very tight schedule what we have for these 2.5 days to fit in all the different infrastructure maintenance and also our own maintenance things here, magnets, vacuum, and so on. But the feasibility was successfully demonstrated this year, and we will go on in this style also next year. So what you can see here, this is our beam time schedule in the second half of 2012. We are around here, so the machine is running and irradiating patients. So the most time is dedicated to patient treatment from normally Monday to Saturday. Sometimes every 2-3 weeks we have a maintenance, short maintenance interruption on Mondays, a half Monday. The rest is then dedicated to other things. This is just to have the possibility to react on short problems, and as we are still commissioning the gantry, a lot of installations are done on these Mondays. So we think in the next year that we can minimize also these maintenance Mondays from every 2 to every 3-4 weeks. Okay, this is the overall plan, and this is how a day at HIT looks like on the 24-hour clock. So let's start here at 6 o'clock. Then our medical physicist colleagues come and do 2 hours of quality assurance. So they check the whole treatment, irradiation, things from workflow, from dose distributions here. This is a typical film that they make in the morning, one at each place, and so on and so on. So this took about 2 hours for the 2 horizontal places in the moment. Then from 8 to 8 we have the patient treatment. And after that, in the evening, beginning night, there is a slot of 2 to 3 hours for plan verification. What is it? So you can see the measurement technique for that. So this is a water basin with a stack of ionization chambers which measure the dose distribution point by point. And so any plan who is put afterwards to a patient is checked with this measurement technique in the moment, just to assure that the plan is feasible, that it is good running, that the dose distribution is correct, and so on. I don't think that we will do that for all plans in future, so we are working on a software check who can do a lot of things in before, but nevertheless, plan verification is a very important thing. Well, the rest of the night was then in the last times dedicated to gantry commissioning mainly. It's on the accelerator side and on the medical physicist side. And then we come to this point. This is our slang. Therapy protocols is the quality assurance that we do on the accelerator side any day. But I showed you that we check the intensities, the position and profiles of the beam. This is done every day, and included in this time is also the retuning of the intensity if necessary. And from 4 to 6 in the morning, there's a slot for biophysics experiments. We have this experimental area, which is away from all the other treatment rooms, but has the same techniques as our treatment room. So you have the full scanning system, everything is there. You could have treated patients there, but this is dedicated only to experiments. And it's clear when the gantry will come into operation that this slot will vanish, or it will be less, but the therapy protocols and the quality assurance, they will put this time and also some more experiments. Okay, so this clock has a 24/7 day rotation, and 2 operators from our team are on shift around the clock. Okay, what is the statistics which I can show to you of these starting in 2007? So the total shifts, we started with around a little bit more than 600 at that time. But a year later, or let's say in 2009, we had more or less achieved the total rate, which is possible without the maintenance shifts needed, so something more than 1,000 shifts per year. And you see the operation days corresponding to that. So the treatment days started in 2009, and they are also settling now to about 260, 270 days per year. We can do something more when we would use Sunday, but this is not foreseen in the moment, but could be done. It's under discussion. So, and then we started with patient treatment this year. Last year we had a little bit more than 400 patients. This year we aim at about 600, 650, a little bit more next year, but there will be a big major upgrade of the particle irradiation facility software from Siemens at the both horizontal places. And as I told you yesterday, the regression tests for a medical product after a severe upgrade is a long story. So this will take really months to run that in and to verify that everything is as good as before or even better. This is dedicated to a better workflow, to shorter times for the irradiation, which they can do in their system, not linked to the accelerator. So, and what we hope is that in 2014, and I think we can be very hopefully for that, we want to achieve 1,000 patient treatments. A patient treated in the year 2014. I think this is a realistic goal, and everything beyond that we will see if it's possible. This is a number that some people have in mind, but 1,000 was what in our proposal from 1999 or 2000 was proposed, and this is, I think, a good goal for a facility with 3 treatment places. Okay, so this story is not at an end, so we will not do only operations, so we are looking for enhancements of our facility and what we are doing now. The goal is always reducing dead times in the synchrotron cycle on our side, so to shrink the time needed for the refilling machine and so on and so on. So one thing what we have seen is that there are magnetic effects one can work on. We have dipoles with eddy currents. So in this curve A, this red one, you see the magnetic field error enlarged by a factor of 1,000. And you see that during the acceleration there is something going on, especially at the end of the acceleration. This is this point here. The deviation is at the maximum, and then the eddy currents die out. And when the field reaches the good field area, which is this green area marked here, then we can extract the beam stable to the patient area. But this time is about 700 milliseconds, and well, you waste this time in any cycle, and this was not a good situation. So we looked around, and there was a development at GSI, an older development which never come into operation, to have a control system for these magnetic fields. And we found that very valuable, and then we put this old development and go back to that, found out where are the errors, where are the problems, and now build a system for that. So this is a normal situation. You have your central control system, you have a power supply for the dipoles in the synchrotron. You put a set value to that power supply, and that leads to a current in the magnet. Okay, the current is controlled by the DCCT, and then it's regulated. So this is a normal system we had before. Now we added a hole probe here for a starting value at the injection level for the magnetic field, and we had a pickup coil that we integrate these signals from in our heat integrator, as we call it. This is a delicate piece of electronics. I can show you only the front plate. What we have done is that we have retrofit this normal feed-forward system now to a control system where a pickup coil, a Hall sensor, and this integrator control everything. And what you can see here is the outcome. This is now the blue curve of the magnetic field. And what you really see here, at the end of the acceleration, we have still a little bit, we are still a little bit outside the good field area, but this is only milliseconds. So after about 20, 30 milliseconds, we can directly, after the acceleration, now begin to extract the particles. And we started this system after doing all the certification, risk management, and all these things which you have to do in such a facility at the end of 2011. The long-term stability was defined as plus minus 1 millimeter of the overall position in the ring of the beams. And what we found out, we fulfilled this rule. There was only 1 point outside after a maintenance interruption. But we fulfilled this rule. The long-term stability is now successfully demonstrated. And as I said, it's a time saving per synchrotron cycle of 700 milliseconds. And you can really, the medical people really told us at the beginning of this year, oh, we feel that we save half a minute per patient, and this is a good story. Okay, but we are not at an end with magnetic field control. When you look to the normal synchrotron cycle, what we have to do in the moment is not to have only the red curve, so we have to make a washing procedure, as it is the accelerator slang. So we go to the saturation just to get rid of hysteresis effects. This is not only for the dipoles, but especially also for the quadrupole. The fact that we have to do that, otherwise we never would have a stable beam at the treatment place. The height and the length of this part of the curve is depending clearly from the energy that you have to achieve for this for the actual slice you irradiate. But the time savings overall would be 950 milliseconds, as we have estimated. We are working on these magnetic field control systems now for the 4 groups of quadrupoles inside the ring. It's a little bit more delicate as for the dipoles, but nevertheless we are sure that we can put it into operation end of this year, and that this would save a lot of time anymore. So to get rid of dead times is really a struggle, but it makes sense because it minimizes the irradiation time, and especially the patient feel more comfortable if it's shorter than today. Okay, another thing we can do is to adapt our scan beam and the mechanism for that with so-called dynamic intensity control. Here you see the animation which Siemens did for advertisement some years ago. You see these slices of a tumor, and then you see the painting, the scanning, the overlapping of the voxels, which is done there. But the film is not really good, because it shows more or less that there is a linear behavior of the speed of the voxel filling, which is not the case. So we will see that. But keep in mind, treatment time per voxel is in the order of some milliseconds. Oh. So keep that in mind. We come back to that in a minute. So we use, as I said, two-dimensional scanned beams for the tumor treatment. And what we have normally in our spill is a shape like this. So it's more or less rectangular, but there are still some parts of the spill which we do not feel really good, that they behave really good, especially the increasing part of the spill is too slow for the medical irradiation facility and technique. So sometimes we get interlocks at that time, because there is too low current in the ionization chamber monitor before in front of the patient. So there is one goal to rise up the beam spill very fast, and then to make it into a rectangular shape. To do that with the parameters I showed you yesterday is nearly impossible, because the filling of the machine is not cycle by cycle the same, so you have to react on that. And okay, this is a classical example to adapt a control mechanism, and we have done that, and you can see what comes out afterwards. You can form a really rectangular shape with a very steep rise of the beam. But if you can regulate the beam to a rectangular shape, then the next idea is, then you can adapt it to what is needed during the plan during the irradiation of one slice. So to adapt it to the particular treatment plan, and this is under development now. I show you that in the following slides. The required dose in one slice does not look flat. So it's, if you imagine a tumor which looks like a ball, and you irradiate it slices by slices, so the areas are getting bigger and bigger, you accumulate dose in the middle, and at the edges you have to adapt a lot of more dose in each slice if you're coming deeper and deeper into the tumor. So you have a high dynamic what you need in the irradiation of one slice. What you do in the moment, you look for the minimum dose in such a slice, adapt your beam intensity to that you can fulfill a dose accuracy of 1 to 2%. And if you come then to higher dose voxels, then you need a lot of time, because you paint them with a very small intensity. And this costs time. So the idea is, why not raise the intensity dynamically? You know the plan, you know what to do. You could adapt the intensity on these voxels to irradiate them with higher intensities. And we started, this was one of the first examples and measurements we had. We started to give a curve of different intensities as a control value to our extraction system, to the RF knockout exciter, and looked how fast will the extraction react on that. What you can see is that the reaction when giving a higher value, Sol value for the intensity, it comes out very quickly. But if you go back to a lower intensity, then you have a relaxation phase, because you have excited a lot of particles during that time. And when you stop, or if you reduce the amplitude of the knockout exciter, still these excited particles are in the machine and they come out. So what you have to do is now, when you want to irradiate such slices and you want to vary the intensity, you have to keep that in mind when you model the data that you gave to your irradiation technique. You have to keep in mind these die-out times and relaxation times. And all this is now modeled and given in. What is the gain of all is that we have simulated and also demonstrated at the experimental place that we can have, depending on the individual treatment plan, a time savement of 20 to 40%. This is really much, and the implementation is now foreseen in 2013. It takes a while because some of the implementation part is not in the machine control system, but also on the medical side, and this takes always a lot of time. But nevertheless, we will have that in 2013, and this will really give us a step forward in minimizing the treatment time. Well, and there is also another idea. You remember this slide which I showed to you, and clearly the synchrotron acts in such a way that you have a discontinuous DC beam. You have to refill after each cycle for the next energy slice in the moment. And well, when you compare that to cyclones, they have a persisting CW beam. They have only the time that they need for switching the energy selector and for switching the high energy beam transfer line magnets to the next energy steps. At PSI, they shuffle to do that in nearly 50 to 100 milliseconds. So why not thinking about doing the same in a synchrotron? And our Japanese colleagues are at the frontier now. They said, okay, this is an old scheme what was developed at accelerator facilities to de-accelerate beam in a machine. And if we could have more than one flat top with one energy in one cycle, we can save a lot of time. For the normal treatment, we have not enough intensity to do, let's say, 5 to 10 energy steps in one machine cycle. So why not doing that? The development is ongoing at HIMEC, and we will start with that also next year. They have, because of restrictions of their control system, implemented now a fixed pattern of energies where they can stepwise de-accelerate the beam from the maximum. And then they can enlarge 1 or 2 or 3 of these fixed pattern energies, and you can see that here. You see the acceleration, then if you come near, you see that some steps here, that it goes down, also in energy, also in the current in the machine. And then they enlarge one of these energy flat tops and bring out the beam. This is what they have done in the moment. It works. Well, you have to invest a lot in the acceleration physics for that, but it is a known technique to do such things. But I think there will be a substantial extension of the control system necessary to have the needed flexibility, because any treatment plan for a patient looks not the same as the other. So you have to choose your energies as you want, not a fixed pattern. But okay, this is the first step they have done, and well, we have to see to follow them. because what you can really gain would be if you come to, let's say, 10 cycles that you can put into one, then you would save so much time that we can really compare with the cyclotron afterwards, more or less. Okay, so at last, an outlook to the latest developments, new accelerator concepts, and superconducting gantries. The latest development of this year coming up into operation are so-called high-field superconducting cyclotrons. What they have done, they used your LHC cables to form a magnet for the main magnet of a cyclotron. And as you can see here, this 250 MeV synchro cyclotron, so it's a pulse machine, has only a diameter of 1.5. It's very compact. It's very lightweight for a synchrotron. But as you can see on the next slide, I have to go back then. They introduced that into a gantry arm. Here at that place, the machine is included. And from the cyclotron to the patient, there is only a gap of, let's say, 2 meters, 2.5 meters, or something like that. In this short gap, the energy selection must be done. The scattering must be done because they use only scattering techniques. So what about the neutron background? I have no numbers. There are some doubts of experts of cyclotrons. But nevertheless, as it's written down, and I found it on official papers, the certification of FDA and also of the Medical Device Directorate in Europe is done, and the first installation is nearly finished in St. Louis in US, and they will start up with this setting in October, November this year. And well, what now is possible is a single room solution, which a lot of hospitals are looking for, because they have not so much patient to fill an institute like ours with 3 or 4 treatment places and 1,000 or 1,500 patients per year. And the investment cost is much too high. So such facilities, the price is about $30 million US. This is something that a large hospital can afford to have one room facility. So it's a step forward with some doubts on the neutron background, but nevertheless it's certified and it will go into operation now. And I read that a lot of hospitals are now interested to have copies of this. Okay, let's turn to new accelerator concepts. A lot of things are sort of and going around. So FFAGs is something which is underway in a lot of countries. Why? It said that, okay, if you have a cyclotron, you have a fixed frequency, a fixed field. This is an easy machine. Synchrotron is complex because you have to vary the B field and the frequency. So a compromise of that is an FFAG accelerator with a constant B field, large apertures, and only the frequency varying. I have my doubts if this is really a good idea. As you can see, the machines are not smaller than a synchrotron, and they are the filling with magnets is also the same as for a synchrotron. And the announcement to have a compact footprint is not really the case. If you look to all these different developments now, then you also find that you need not only one ring, you need at least 2 or sometimes 3 to come up to these high energies, which we need 220 MeV for protons or 430 for carbon beams. And there are a lot of questions. What about the variable energy extraction? These are pulse machines, how you can go to very high repetition rates if you want to have scanning techniques and not only scattering. There is a worldwide high interest, so there are a lot of projects around, but I think it's not the right adaptation for particle therapy, maybe for other purposes. Well, and clearly when some years ago these laser plasma accelerators were developed and came out, where you use a very high power laser going to the petawatt regime with very short pulses, 50 joule per pulse, high intensities, working in such a manner that you put a laser pulse on a foil, you generate a burst of high energetic electrons, and if you put on this titanium foil, this was this example here, a proton-rich dot on the back side, then these electrons, when they are crossing this spot, they also accelerate protons. And then you have a bunch of protons here. This is a more 3D animation of that. So what was achieved, or what they want to achieve, is 10 to 11 protons up to 300 MeV. This should be possible with petawatt lasers. My last number, which I found really in the paper, was 67 MeV at the end of 2009. I think the development has gone forward. So I heard about 180 MeV that would have been reached and so on. But nevertheless, there are still some open questions how to use this technique. One question is a repetition rate. And until now, these laser systems need minutes and hours to have the next pulse in the moment. So there has to be something going on. And the second thing, very important for irradiation of treatments, is the intensity control. I have my doubts. That would be a long story to make that. And sometimes you found this really science fiction proposals like this one. Someone compared our gantry with a small gantry setup laser. You bend the laser around and then you have the laser focus spot 2 meters away from the patient. I found this is really science fiction, yeah. Because I have my doubts that you can have monoenergetic beams in such a configuration. Again, you will have the problem with radiation background and so on and so on. But there are some other activities underway which are more serious than that. So one of that, just one example from Germany, is the Oncoray in Dresden. They have a 150 terawatt laser called Draco, which will be extended in near future to 500 terawatt, and then they want to go to the petawatt regime in the next years. And they have done something very interesting. So they are building now a new facility which houses a really normal cyclotron, one of these IBA bread and butter machines, and they have one therapy area that they want to use together with a hospital nearby. So they will have people who do all the normal operation to irradiate patients. And within this facility, they have their laser to make research, and then they will have the possibility later on to make a connection here to send the beam from the laser to also to this therapy area. They use only scattering, not more, but nevertheless, they want to do the turnover from the normal cyclotron operation to the laser within the next 10 years. I wait. They can afford that, but we will see what is going on. So it's this would shrink clearly, dramatically, not the size, but the possibility to make things cheaper. Because this laser arrangement, the numbers, the costs for that shrink year by year. So we will see what comes out. So I'm very optimistic that we will see in 10 or 15 years the first facilities driven by laser accelerators. And another concept which is going around and is always discussed for people when they spoke about proton therapy is this so-called dielectric wall accelerators. The patent holder for that is Mr. Caporaso from Livermore. And they say maybe one can build such injector modules with high gradient accelerator modules of 500 kV in millimeters. I have seen this sentence, hoping to build a full-scale prototype soon, now since years, but nothing appeared now. But still, this concept is underway. You should know that. So, and there are some really nice animations you can see for this very short things. But okay, I have my doubts that it will see such a full-scale prototype in the next 10 years. Okay, last 5 minutes to the topic design of superconducting gantries. It's clear if you have carbon and you have protons, you have magnetic rigidities going up to 6.5 Tesla meter. And if you have a normal dipole as we use them, then you need a large bending radius of more than 3.5 meters. If you could do this with a superconducting dipole with a field of 3.3 Tesla, this is not the maximum you can do, but it's a good value to achieve, then you can reduce that. And there are 2 design studies underway in the moment. One came from the fact that the HIMAC gantry for the ions, which they want to build normal conducting, was not financed, but the hall is there. And so they have now some years to think about it to make it better. And they started a program and they said, okay, we can make a more compact gantry using superconducting magnets. And what they want to achieve now is a radius which is only 5.5 meters. The length is only 30 meters, 3 Tesla magnets. So this is a conservative idea. A little bit more going higher to higher dipole fields was done in a study in France together with IBA. You can see the outcome here. Clearly in all these projects, it's foreseen not to have liquid helium, but to use cryocoolers. But then you have a long time for cooling down these constructions. And especially in the case of quenches, you have long recovery times. I think I read a number of some hours after a quench in this configuration in the paper I found on that. So this is a slide of the Japanese version, how they would put that together. And just to show you, the schematic is the same as in our case at HIT. So you have 2 45-degree magnets, and then you have a cascade of superconducting magnets at the end here of 22.5 degrees for 4 pieces of that. And well, they are really underway to build these magnets because this is a delicate thing. No one had done this before, to have this curved magnets with this small curvature. Well, it's underway. These are photographs of March 2012. I have no newer information about that, but the first things are underway. They want to use low temperature superconductivity. But another idea was studied in the last 3 years in a small project that was financed by the Danish government and was done by the Danish company Danphysik. They made a prototype of high TC via magnet. It's still straight. It's not curved, but but it was a small prototype. It aimed at 3.6 Tesla, and they could achieve that after some while. And it would work at about 15 to 20 Kelvin, which makes the cryogenics a little bit more relaxed. They also have used cryocoolers. The advantage in my view is that in case of quenches, the behavior is much smoother than for these low TC magnets. In the case of high TC, they told me when I visited their facility that they can see how the quench comes, and then they can react much faster and to avoid quenches as good as possible. And also the recovery time is shorter then. So also this is an attempt, and I think there will be a lot of development around the superconducting gantries in the next years. Okay, so I come to my end of this talk. I just want to thank again a lot of people who gave me their publications, their slides, and their what they published in the last years. There are also a lot of companies sent me data, and I have to thank them. And I have to thank you. But before I can included some sources of information. There is a very famous website of the Particle Therapy Cooperative Group, hosted at PSI. Clearly, a lot of papers are also published on the Joint Accelerator Conference website. Then there was a fantastic workshop. I unfortunately couldn't take part of this partner workshop, a EU program, which took here, was settled here at CERN, where also a lot of good information is in, and clearly there is our homepage where you can read something that's also in English. Okay, so I come to the end. Thank you for your attention.
Some questions?
Yes. Yeah.
And the second question about the cost, you need an expert now about cryogenics. So you are adding something for the cost for the operation and so on. So is it really a tendency, or what do you really gain?
Yeah, as you said, so the structure becomes smaller, lighter, cost for that would reduce. On the other side, clearly cost for superconducting magnets would be in the beginning higher than for normal conducting ones. But that we have to see, because the cost for the material and so on are really varying in the moment, so one has to calculate that very carefully. But the main effort is that you have a really shrinking of the hall that you need. As you have to think that we have a hall that is covered around with 2 meters of concrete. Yeah, alone this part of our facility costs some million only for the concrete around. And if you shrink the size, then you can save a lot of costs for the concrete. Okay, comment to cryogenics. Well, I don't think that you really need an expert for cryogenics afterwards to maintain that. The cryocoolers of today are very stable. The technique is used in several areas in the industry. So there was a big development in the last 20 years. And I think if you have a good vacuum engineer, you can learn also to deal with this cryogenic coolers. This is not a big deal. And I think this superconductivity and gantries, this is one of the hottest topics for the next 10 years in particle therapy, especially for our facilities where we use ions and proton beams. For proton alone, I don't know if it's really a story, maybe, but for ion facilities, yes. Let's go back. Yeah. So the length of the radius of our gantry at hit is 6.5 to 7 meters, but the length is 25 meters. So in volume, a factor of 2 is possible, or more. This is depending on this factor, how high you can go with the field, what velocity you can gain because you have to vary the field, which is not so easy in superconducting magnets to do that very fast with high precision. So there are a lot of questions, but I think there is much potential in this question and the developments. And what is the problem of today is to gain money for some prototype magnets and later on for a prototype facility. Because the whole topic, particle therapy, today has moved partly from the institutes now to the companies. And this is well, you would need, I would say, let's say 20, 30 million for a prototype study with a full-time, with a full-scale model at the end. We will see who can afford these investments. We will see. Okay.
More questions?
Yeah.
I share all your doubts about these novel technologies. I wrote to Caporazzo 2 years ago because I had to give a seminar. He never even replied. The medium system. I was in contact with Mr. River a couple of times. They gave me material. They claim they can do scanning with their device, which also have a little bit of doubts. In any case, the machine is like that. So it's going to be fixed energy, I guess. And they will have a passive trigger for modulating. I don't think there's any way out. You said they plan to use passive scatter. So do you have any more information? Because I mean, using now a new installation, using passive scatter, not going to scan it for me, doesn't make much sense. Do you have more information about it?
No. Everything which I have as information was on my slides. So if you go to the new web page of this company, which is now called Mevion, you really did not find anything of techniques. Yeah, so you have to look around in the internet to find some. I got some slides from Eros Petroni from BSI, and so you have to look around to find these. You say it makes no sense to go back to scattering. Well, for a scientist, from the scientist's view, yes, you are right. But medical people think in another way. They are very conservative. And a system which has a scattered beam with a multi-leaf collimator is not a nice system, but it works.
Yeah, well, I mean,
and you can do that. You can treat patients with that, and you have a proton beam instead of X-rays. So you gain going from X-rays to proton, but not with the best technique, but you gain. And this, and at the end, always the story in when you go to hospitals is this is costs, and the one-room installation is what the market wants.
I know, but that costs 30 million. So tomotherapy costs 2 or 3 million. Yeah. And tomotherapy can do quite well.
Yeah, clearly. So
this is why I'm down.
I don't know where it's going, but I read that there are a lot of hospitals now ordering or looking for this one-room machine because they say we need a facility which can deal with 300, 400, 500 patients per year, not more, and we could not afford an investment of 100 or 150 million. So this is the story.
But even a hospital has enough money to build 4 rooms. If you have 4 machines, one breaks down, it's 3 rooms.
Yeah.
You know, if a single breaks down, then you're stopped.
This is a totally other story which we discuss internally every half year, what to do when we have a really big break in the synchrotron. So this would be dramatic. But okay, so we have to do we do our best that it never would appear. but we are not sure that this will not happen clearly here. If you have like in the normal X-ray treatment, you have 4, 6 linear accelerators in parallel. This is not a story, but if you have only one synchrotron, then it's a story clearly. Okay, so thank